Okay, do you hear me? Oh, sure. Hi everyone, my name is Eyal Post. I'm working at a company called Gett, and at least once a week someone tells me, how come you're a post and you work in Gett? So I'm used to it. And I've been in the software industry for about 20 years now. Did a lot of different jobs, starting from a developer, senior developer, architect, and today I'm an architect at Gett. I'm also very happy to be here, and thanks for having me, allowing me to escape from the Israeli weather for a few days. So a few words about Gett. Gett is basically changing the way people move around and get things. We're not only a taxi hailing app, we also have other services. We provide shuttle services, delivery services. We actually have a service called Gett Post, which I should have been there in the picture, but someone thought it wasn't appropriate, and it allows you to get your post office deliveries from using our service, using Gett. Until about 18 months ago, Ruby was our main language when we started using Go for some of our services. And about 6 months ago, we decided that all new development was exclusively in Go. And before I tell you why we decided that, I'll tell you a short story. About 20 years ago, I was visiting Germany, and I bought a camera there, and the salesperson told me, listen, if you are going to cross the border, you can get a tax refund for your camera. And I was actually on a trip, so when I crossed to Switzerland, I went to the custom office there and entered this very large hall. There were 2 lines there. Everything is very quiet. I was standing in one of the lines because I didn't know to read the signs. And when I got to the clerk there, he told me, what do you need? I told him I need the tax refund. He said, okay, but you're in the wrong line. You should stand here. And I'm looking at the other line. It's already 10 people there. I said, this line? He says, no, there's a line in between. So I'm telling him, but there's no one there. He says, don't worry, someone will come. Okay, so I'm going to the middle line, waiting there, feeling a bit stupid, standing by myself with no clerk there. After a few minutes, the clerk finished servicing the guys in his line. He gets up from his chair, moves to this line, and asks me, yes, sir, how can I help you? So if you're coming from Israel, you know we are not good at standing in lines, and we are definitely not good in moving between lines when not needed. So for me, this was a very unusual experience. And why am I telling you this? Because I'm going to use this metaphor of people standing in lines to see how Go works and how it compares to other runtimes. So the first thing I want to talk to you about is the sit and K problem. Anyone heard of this term? Raise your hand. Okay, great. So the sit and K problem is basically started by a paper that a guy named Dan Kegel wrote about in about 2000, about how do you handle 10,000 concurrent connections on a single server. And back then, the default model for handling such cases was a thread per connection. Right? If you look at, for example, Apache web servers, when a client connects, the server creates a thread, and that thread handles all the communication with this client. If we go back to this analogy, it means you have a lot of queues, only 2 clerks, and these clerks need to switch between those queues. A person comes to the clerk, he asks something, the clerk might, even in the middle of work, move to another queue, handle it, and then go back. It allows you to use a lot of queues, and it simulates concurrency by people handling, by these clerks handling those multiple queues. So what are the issues with thread per connection? Well, in terms of CPU, thread switching, we know it's a very expensive operation. If you are creating 10,000 threads for 10,000 connection, the CPU wastes a lot of time just by thread switching. In terms of memory, we are basically creating a stack for each thread. So if you are creating 10,000 stacks, it's going to waste a lot of memory just to handle those threads. And in terms of I/O, in most servers today, most of the activity that the server does is basically I/O. It calls another Redis server, it will call the database server, or maybe it will send a request to another microservice. Most of the time, it's doing a lot of I/O. So you are creating a lot of threads, and these threads are most of the time just idle, waiting for I/O responses. So what other options do we have? So for example, we have Node.js that we know handles that well. Nginx, what's the difference between Node.js and other servers? Anyone has a quick answer about that? Sorry? Exactly. So those servers use event loops. They are single-threaded, and they work like this. Basically, you have a single thread handling all kinds of events. Each event is a different completion event. Basically, when a timer expires, some code is run. When an I/O completes, some code is run. And Node.js basically runs through all those steps one by one and perform those callbacks. And the idea is that Node.js, the code itself is always CPU bound, right? If you are doing I/O, it's done in the background. This single thread is always doing CPU bound work. And Node.js uses a library called libuv, and basically, if you're doing file I/O, it goes to some thread pool. If you're doing network I/O, it goes to the native asynchronous operating system APIs. And if we look at this analogy, it's basically like a single clerk handling all those requests. Each queue is a different type of queue. They are not the same like we saw in the previous picture. A person comes to a queue, he knows that he needs to stand in that queue, the clerk serves him. If this person needs, for example, to fill a form, the clerk will tell him, okay, go to the side, fill that form, and when you are finished with that, go back to this queue. How does Node.js code looks like? We all know that. It looks like it's sequential, but actually, it doesn't run sequentially. Using callbacks, we are managing I/O completion. So what are the problems, or what are the benefits for Node.js? In terms of CPU, we are using a single thread. There's no thread switching overhead. In terms of memory, again, single thread, only a single stack. So it's not taking a lot of memory like the previous models. And in terms of I/O, the CPU is never idle waiting for I/O, right? I/O is always done in the background, and the event loop gets notified when I/O completes. But the problem with Node.js is that CPU-intensive code can block the event loop, right? If someone comes to a clerk and starts discussing with him, takes a lot of time, everyone waits for this to complete. And actually, we're not making good use of multi-cores, right? We have a single-threaded application. Even if we have an 8 or 32 cores CPU, we're not really using it. We need to spin several Node.js instances in order to make best use of our resources. And the code, I mean, people are getting accustomed to writing callback-based code, but as developer, we all prefer to work sequentially, right? If we could just write the code sequentially and let someone else handle all those callbacks and all those async calls, it would be better. Node.js basically took a technical detail of the operating system and how it works, and asked us as developers to handle it by writing code differently. So, and actually, one of our busiest services in Gett is a service called driver location, and about 2 years ago we wrote it in Node.js because we had scalability issues with Ruby, and Node.js served us pretty good back then. So how does Go work differently? I mean, we all know that Go uses Go routines, right? We can create a lot of Go routines. How does it solve the problems that I mentioned before? If we are creating 10,000 Go routines, then all the problems that we had with threads probably will happen in Go, right? So not really. Let's look at how it works. So the first thing I want to talk to you about is stacks. How does Go handle the stack? Why do we need a stack at all? Why do we need a stack? Local variables, right? What else? Parameters to functions, correct? So local variables, parameters, return values, they are all kept on the stack. The way operating system stacks work is that they are fixed size, right? When a thread is created, the operating system creates a stack for this thread. What size should we create this stack? If we create a stack which is too small, then we are risking stack overflow, right? If we are calling a function recursively and passing parameters, the stack gets filled. If you pass the stack size, you get a stack overflow exception. If you're using a very large stack, then it's a lot of overhead, right? If we look at the sit and k problem, if you are creating 10,000 threads, if you're using a 1 megabyte stack, which is the default in most operating systems, you're basically wasting 10 gigabytes of space just to handle stack space, even if those threads will never use most of this stack. So how does Go solve this? Let's look at a very simple function. Basically, get two numbers and return the sum. Let's look at how the assembly code for that function looks like. So to see the assembly code, I'm building the binary without optimization, so it will be easier to look at the code. I'm using a tool called optdump, and I'm passing the name of the function that I want to look at. This is the code. Don't worry. I'm just trying to show that it maps exactly to how the code looks. So the first part is the A parameter. The second line is the B parameter. We are doing an add operation, moving that to the return value and returning. Okay, that looks simple, makes sense. What if I add another call in that function? Let's look at the assembly code now. So this part of the assembly code is almost exactly as we saw before. This part is the one that calls the new function I added, the log function. But there's also this part, which is not mapped to any of the code that I actually wrote there in the function, right? So the first time I saw that, I tried to understand what this code does. Let's follow it. So we are comparing some register to the stack pointer. If it's below some threshold, it jumps to this place. We are calling a function called moreStack, and we are basically going back to the start of the function and running the function again. So what is moreStack? It's exactly what you think. The Go routine stacks basically starts very small. The default is 2 kilobytes per Go routine stack, and it grows as needed. And actually, it also shrinks. So if you call a recursive function and then the function returns and you no longer need that stack size, the GC will notice that and will shrink the stack. So if we are creating 10,000 Go routines, each one 2 kilobytes, we are only wasting 20 megabytes of memory for stack size. So Go routines are much more efficient than threads for stack memory. Okay, so what happens if we are not calling a function, if we are allocating an array inside that function? Okay, we saw that only when we call the function, the compiler injects this code which checks stack sizes. So let's say I'm allocating memory. Couldn't it also cross the threshold and cause a stack overflow? Well, actually, the compiler detects exactly when it's needed and when it's not. So if I'm allocating in this place 100 bytes array, the compiler we'll know that there's never a chance that we'll actually pass the stack threshold. It will not generate any additional code. If I'll change that to 105 bytes, this is when the compiler sees that, okay, there's a chance that you are going to need more space, and it will inject the stack expanding code. So it's basically, if we're looking at managing people in queues, it's like moving from this kind of separators between queues that are fixed size, that are made of steel, you cannot change them, to something like that, which is elastic. The more when the queue grows up, you just put more separators. Okay, so the next subject I want to talk about is the Go scheduler. So how do Go routines get scheduled? Let's look at some code. It looks complicated, but it's actually very simple. I have a loop creating several Go routines according to this parameter. And inside those Go routines, I'm trying just to increment a progress variable, okay? So I'm running in a tight loop, just checking whether someone told me to stop. And until someone tells me to stop, I'm just incrementing this variable. It's basically this code. This is the simple version, but this is a thread-safe way, okay? So while not done, increment the progress and display how much we got. So it's basically like a horse race, right? I'm telling all those Go routines start running, and at some point I'm telling all of them to stop, and I'm seeing the progress between those Go routines. The idea was to see how the Go scheduler works. Does it give equal time to each Go routine? How much increments can they make? So the first time I ran it with 2 Go routines. This is the progress I got, 500,000 increments. Okay, that's not really interesting. 3 Go routines, I got to about 1 million increments. And when I ran it with 4 Go routines, I was a bit surprised. Anyone can tell what was the output? No one can guess? Good. So this is what I got. I was waiting for it to end, and waiting, and it just never ended. So I went back to the code, tried to understand what was wrong with my code. Nothing wrong. I ran it with 3 Go routines. Everything works perfectly. I ran it with 4 Go routines. I got 100 CPU usage, and the program was stuck. And why is that? So let's compare, to understand that, let's compare between threads and Go routines. So we said that threads are scheduled by the operating system, and Go routines are scheduled by the Go runtime, right? Thread can switch at any point. That's what we call preemptive scheduling. Basically, the operating system takes a thread, whatever it is doing at the moment, it doesn't matter. It can put it aside, save all its state, take another thread, and tell it to run. But Go routines, they are scheduled by the Go runtime. So they are scheduled cooperatively. What does that mean? It means that basically a Go routine needs to ask the scheduler, can I continue to run? Should I switch to another thread or a Go routine? That's what we call cooperative, because the Go routines needs to cooperate with the scheduler. So we saw that they are only allowed to switch at specific points. What are these specific points? If a Go routine does I/O, this is the place where the Go scheduler will check if it needs to pass Go routines to another Go routine. If it's doing send or receive on channels, that's a switching point. If it calls a sleep function, that's the best place to switch to another Go routine, right? So if we look at this code, there's just no switching point here, right? You are running in a tight loop. There's no way for the scheduler to tell you to signal this Go routine, listen, you need to pause and move your time to another Go routine. So how can I solve that? For example, in this case, I can just call sleep 0 and run it again. And this time, the scheduler will have the opportunity to move to another Go routine, and everything will finish as usual. And probably you saw in the previous slide that I said that this was stuck on a 4 CPU machine, right? That's why at 4 Go routines it got stuck, because all those 4 Go routines use the entire CPU. There is no other thread available to actually check and switch the Go routines. So when I was playing with that, trying to see at what points it can switch to another Go routine, I called a few functions, and I noticed that if I'm calling a function called do something, which call a function called do nothing, which actually does nothing, again, the thread switching works correctly. So how does that work? We don't have any I/O or channel send and receive. So what I found that another spot where Go routines can change is this part of code. Remember this one? It's the code that was used to expand the stack. So actually, the Go scheduler will put some magic value inside the stack threshold, and when the function starts and it has this code, it will think that it needs to expand the stack. It will jump to the more stack function. In the more stack function, it will notice that actually it doesn't need to expand the stack. It was just a signal for it to stop, and then it will ask the scheduler to move to another Go routine. So context switching also happens during stack checks. And that is why a lot of people ask me, okay, so isn't it dangerous that Go doesn't have a place to switch to another Go routines? As long as your code is not just a loop doing increments, most chances are you will call a function, and that function will have that stack check within it, so everything will work as usual. So we saw that there is another, we talked about thread switching and how expensive it is, and I want to explain the reasons. So we know that threads, the scheduler is not aware of the actual code running inside those threads, and the difference with Go routines is that the scheduler is aware of the code. And why does it matter? We said that thread switching is expensive. It's expensive because it can occur at any time. The operating system does not care what kind of code runs inside the thread. It doesn't really know. It could be C code, it could be Java code. For the scheduler, it's just assembly code. It needs to take that thread, put it aside, save the entire thread state. And what does it mean to save the entire thread state? It basically means to take all the registers currently in the CPU and save them aside. And the operating system does not know exactly which registers are being used, right? Modern CPUs today have a lot of registers. Most of them are very large in size. Taking all those registers and saving them aside might take a lot of time. And how does Go routines behave differently? Well, the idea is that the compiler, which actually generates the Go code, knows exactly what is being used. And the Go code, the assembly code generated by the Go compiler, simply uses 3 registers to handle all the Go runtime. So when you're switching a thread, all you need to do is save those 3 registers aside and put another Go routine to run. That's a lot of differences, a large difference between taking all the registers of the CPU and putting them aside. Okay, but what happens? We said that Go routines actually run behind the scenes with a thread. What happens if a Go routine does a call which blocks? We are suddenly blocking that thread, and we have only three threads left, and we need to find a way to run other Go routines. How does that work? Sorry. So let's, for example, say that my Go routine took a mutex and locked it, and is waiting for that mutex to be freed. What happens? Does it actually lock the thread? So the fact is that Go does not use native operating system mutexes. It uses something which is called a futex, which is a user space mutex. And basically that helps it to never really block the thread. If you are taking that mutex, you're basically telling the Go scheduler, listen, I'm waiting for this mutex to be freed. Park me aside and let me know when this mutex is free and schedule my Go routine again. So the thread is never blocked in this case. What happens with file I/O and syscalls? Well, it is handled by additional threads. If a Go routine is about to make a file I/O operation, it will notify the Go scheduler, listen, I'm going to make a file I/O, it may take time, please pin another thread, so there will always be another thread free to handle Go routines. And network I/O, this is handled by a subsystem of the Go runtime called the netpoller, which is basically a single event loop, just like Node.js. But instead of scheduling stack callbacks, it's actually scheduling Go routines. So when the code is making network I/O, it's basically calling the asynchronous APIs we saw before, the native asynchronous APIs. And it lets you write sequential code, but behind the scenes it uses a single event loop which calls Go routines. So we see that if we compare Node.js to Go, the general architecture is very much the same. Network I/O is handled by native async APIs, just like in Go. File I/O is handled by a thread pool or a thread cache in Go. So they are very similar, but at least in Go, you write the program as a bunch of sequential commands instead of using callbacks. So how do we compare that to the other drawings we saw? So this will never work in Israel. You need this guy here. And he will tell each people in each queue to which thread to run. So these are Go routines, these are threads, and the scheduler is responsible to tell someone from each queue to which clerk to go. If someone needs to fill forms, for example, the clerk will tell him, okay, go back to your queue, I will handle someone else, and everything works as usual. So how does it work in terms of CPU, memory, and I/O? So for CPU, we are using number of threads is approximately like number of CPU cores. We are using all the cores available in the CPU, so we are making good use of CPU resources. In terms of memory, we do create a stack for each Go routine, but those stacks start very small, so they are not taking a lot of space, and they are only growing when needed. And in terms of I/O, we are actually doing asynchronous APIs, which are the recommended way to make I/O calls in very heavy servers, but we are using a synchronous programming model. So when we started to have scaling problems with Node.js, we basically rewrote this service using Go, and today this is our busiest microservice. It handles 2,000 requests per minute with average response time of 2 milliseconds and just a few instances to handle all of that. So let me summarize. We talked about the sit and K problem, how to handle 10,000 connections on a single server. We talked about different threading models. The thread per connection model, which is very simple, but it's not really scalable for very busy servers. We talked about event loops, how they solve the problem of scalability, and how Go solved that from another perspective by using dynamic stack sizes and the scheduler, which is working in the user space scheduler instead of the operating system. So if you are still debating whether to use Go for your next project, talk with me. We have very good experience with Go. It was a language very easy to learn. In just a few weeks, you get up to speed and you know the language good. It's a very compact language, right? It's not like Ruby. There's a lot of operators. Go is very simple. It's very easy to learn. It's fast in production. It's very scalable. It's very easy to deploy. So thank you.
Thank you, Eyal. So, your questions, please.
Hi.
Hi.
I was wondering about the internal representation of the Go routine stacks. Are they just like arrays, and does it have to copy that array when it resizes the stack, or is there some other representation that?
Okay, so actually there's a very good article about that on the Cloudflare blog. If you will search it, there it's actually copied on demand, but it's going to another place that when it's shrinking, it will save the space. So it's not, there was a problem of fragmentation with Go stacks, but I think it was in Go 1.8 that they did a change there, which I don't want to say solve the entire issue, but it makes it a lot of better.
Okay, thanks.
Hi. What's the cost of the stack growing operation, and can I specify the stack size before the call function?
No, you cannot.
What's the cost?
Sorry?
What's the price of stack growing operation?
Basically, the way it works, it always doubles the stack size. So it might be a bit expensive at the start. I mean, if you know in advance that you have a Go routine which uses a lot of space, then at the start it will grow and basically make a few allocation just when you are starting. But if you're not using a lot of stack space, it's not that expensive.
Thank you.
You said that file I/O is done by allocating a new native thread. Yeah. But also you said that most Go routines do I/O most of the time. And for example, if we have a utility, not a network service, and we are doing most of the work is file I/O, then most of our Go routines will have native thread assigned. So what the reason? So is it really blocks on file I/O? Why it is not using asynchronous API?
Well, I think it's the same reason why Node.js doesn't use asynchronous APIs for file I/O. Node.js also uses thread pool for file I/O. And the reason is most I/O that you are doing in your service is usually network I/O and not file I/O. And if you read the Go blog about why they decided to do that, they said that in most cases, if your service is doing a lot of file I/O, then you'll probably be slower with file I/O, and you are actually going to use, so your disk will be slower than your process anyway. Okay, so it doesn't really matter if you are doing asynchronous I/O or thread pools.
I see, thanks.
More questions?
Could you explain how Go returns the memory? Like if you don't need anymore the memory, like does it return it to operation system, or how does it work?
All I know about stack sizes is that it's handled as part of GC. If this memory is returning back to the operating system or not, I'm not sure. Sorry.
I have a question, if there is no anymore. Do you use Go or some Cisco's in your code?
In our case, we never use any Cisco's or Go.
Okay. So that's all. So we have to pick two
best questions, and the lucky ones, their tickets.
You'll take one.
One more question. We have one more question.
Sorry, the other one. Yeah. You. Who asked the question? We have one more question. Okay, you have a good chance to get this one.
Hello. So I've heard that the scheduler worked on work stealing pattern before, and now it works on work sharing. So basically, you have a coroutine which is running those threads, but because of the cooperative
scheduling,
because of this cooperation, the switching is performed very rarely. Could it happen that one coroutine would actually be running inside one thread on, for example, one core, and other ones would be solving?
So I think that's what we saw, right? A single Go routine can saturate a single core and will not be able to switch to other Go routines. It can happen, but it's very rare because there are a lot of switching points in the Go runtime.
So are there any tools to profile that?
I'm not aware of such tools, but if you are calling enough functions in your code, then in most cases you are covered. The thing that I'm worried about, or it will be interesting to see how it will work, is in the next version of Go, there is supposed to be a new inline optimization. So that means that a lot of function will basically be, the code will be written in the parent function, okay? So if you have a small amount of function calls, then there's a chance that there will be a lot of code that will not have any switching point. So this is something I'm waiting for the next version to see how it works, because when Go inlines function, you're basically losing a lot of switching point.
Okay, thank you.
Yeah, sure.
Hi. Hello. You speak about Ruby code in your company backends. How much Ruby code still remains in your company backends, and which is the main problem in rewriting this code? Thank you.
Okay, so we have about, I think, 50-50% Ruby code and Go code now. Most of the Ruby code is our largest monolith, which we are now splitting to microservices. Those microservices will be written in Go. We had quite a few scalability issues with Ruby, specifically in very high performance services. That's the issues we had.
Hello, thank you for your talk. My question is not so technical as others. At the beginning you said that you decided to switch all new development to Go. Mm-hmm. So what was the reaction of the engineers, how they accepted this decision?
I would say it was also 50-50. Some of them really liked it, and some of them were very used to writing Ruby code for years. Today, most of the developers like the language, and some of them will like it eventually.
Thank you.
Hi. I'm here. My question not generally about Go, but what type of technology, what type of communication do you use to handle such load between services?
So actually, most of our communication internally is HTTP based. We're also using RabbitMQ for asynchronous communication. And that's the main protocols we use.
Thank you.
So, okay, last question.
Hello. It looks like Go is really suitable for microservices, but are there situations when you should not use Go for microservices?
I can't think of any situation. I mean, if you want to develop something really fast, you're a very experienced Ruby or Python developer, go ahead and do that. I love Go, so I use it also for very small projects. I don't see a reason. If you think dynamic languages are very suitable for your project, then you can use a dynamic language. If I need to choose between Go and Java, it will only be because, I don't know, the ecosystem of Java is probably still larger than Go. But from what we saw, almost every library we needed for Go, we could find a library existing today.
Do you miss generics?
Yes, I do.
When? For what?
For what?
Yes.
I shouldn't have said that I do miss generics, so I don't.
Okay, so thank you. You have to give the second ticket to somebody.
Thank you.
So thank you, Eyal.